Hello. So today I'm going to discuss about the linear algebra and matrices and why these are important in like real life problems or like real life problems like you mostly deal with when like complex system like a quadrotor or like heavy machineries and or car systems or aeroplane or anything like anything like in case like you want to predict their behavior or like you want to control those things like you want to control the vibrations or you want to control the suspension systems in your way or you want to predict what is going to happen and what action should you take. I think in all of these cases linear algebra and matrices is very important, mostly like a linear algebra combined with the matrices. And previously I never knew like this is really very important. Once I started studying control systems and dynamic systems, I realized how important this is. Like at first it was very difficult for me to grab the concept of like linear algebra and matrices and capturing the system behavior using equations and matrices. How I was thinking like how someone can like represent the systems behavior using equation like x y z 0 1 2 3 4 like this, like using numbers. How can one represent something? It was like so much difficult for me to grab a concept initially. But like eventually I understood the power of the linear algebra and matrices to identify the system and use that one to predict the nature and the behavior of the systems and how to control that one. Actually, like I fully understood that one once I did the project. So I said like it is really important in real life. Like I have worked on the multi-agent systems. You might have seen something like multiple agent working together, like multiple robot working together, communicating each other, like that one. Even in that case, it is really important to have a good understanding of linear algebra and matrices. And I have also worked in like quadrotor and quadrotor dynamics. Like quadrotor is highly nonlinear dynamics, highly nonlinear. Like it have like 6 degrees of freedoms. Like it can goes any side and rotate any directions. So like and move any directions too. So quadrotor is highly nonlinear dynamic systems, and in order to represent this one, we use like rotation matrices and all those things, and it becomes highly nonlinear. So what we do is like we convert the linear system to the linear one, linear, and use linear algebra to find the system, right? Like or to identify the systems once we like able to calculate the motion using the linear algebra. So actually like in order to represent the system, we mostly use the Newton's equation of motion. So Newton's equation of motion most of the time, and that will represent the system. So from there, like using F equal to ma and using inertial terms, and from there once we identify the systems, we convert that one into the like linear algebra equation form, and we represent that system using matrices, and from there we compute the motions, and whatever we want to study we can do for the analysis from there. I have done the project on that once. I will show you that things later in this video. So like so I what I want to say is like this thing is really important. Like if you are solving something very complex and highly like real world problems, like which involves non-linearity all the times, then you really need to know these things. Basically all the things are non-linear, so like you have to convert to the linear system, like break down to the linear systems by assuming something like in case of quadrator you might assume like a rotation angle is like minimum, so it will becomes sin theta will becomes theta, and cos theta will becomes like almost 1, so like that ones, and lots of things like you can assume and predict and identify the system, which is simple to study. So mostly what I'm saying is like these things are used for the simulations, but once you simulate and you want to control the real system accordingly, you can do that once, but sometimes you only have to like tweak some of the parameter or change some of the parameter to get your desired result, but it works in real world too. But there is like lots of other methods you can see, like I'm not talking about any of the methods right now, but there is lots of methods which really solves the nonlinear system too, but in approximate manner, right? But you can solve nonlinear system either. I haven't solved the nonlinear system yet, but I'm planning to do that one. But right now I will talk about this one. So let's see what I have done. um, Over here, no, over here, yeah, over here, like I have used one of the papers, uh, and from there I got these pictures, and in this one he have like a, you see this one is the equation of motions that we have used to represent this quadrotor. And once we represented using the like Newton's equation of motion, and this one we linearized this equation of motions. There's lots of assumptions made over here, so like I did that once just because I had to finish the project within 2 months. So let's see over here, like just like I said, I assumed cosine to the 1 sine e to the theta, and I have only used the 2D position of the quadrotor, so quadrotor will only move in 2D directions. And also the quadrotor is at some height, so quadrotor will only like will not have any effect of the like air when it is on the ground, so it doesn't have effect of the like of air which is forcing from the ground, so it is at some height, so those effects are like simplified. Even gyroscopic effect is simplified over here. But what I want to say is like how linear algebra matrices is important. Let's say over here, once I simplified, I represented the theta and their velocity using the theta and theta dot, and I have also represented this one, this you see, this x theta and u theta and tau theta. I have represented this one using the equation of this one, this equation. So let me okay, this I think you can see the equation 6. Okay, so I have represented using this equation number 6, and in that way like you can like after you can simply I think no, I have done this like you see I have represented this whole equations over this whole equations in this equation form. So like this is equations, it's the same linear algebra equation, but I have written this one into the matrices form. Once I write down the matrix form, now I can use some of the methods and put this matrix value into the into these equations, and I can do anything using that one. You see, this is the result that I got. Like I really felt like so powerful, like how someone predict the real behavior of something using the equation matrices, those things. So I was so much excited. You see, this one in this figure, in the first figure, I'm like there is this one red is the obstacle, and this one is the like I given this dotted blue line is the reference path, and I'm trying to find the optimized path using the equations. So you see this the red path, the red line and the blue line is matching. Like there is very little difference, and they are following the path exactly. And the obstacle is far away, so it is not a problem. But I will show you how it will avoid the obstacle using the equations. It is really fun. So now let me show you. So in this case, like there is something that you need to consider. I am not talking about that one right now, but you see, in this case, I put the obstacle in the path, and it didn't avoid because of that Q and R that is like so much strict, and there is other term too, so it was not able to avoid the obstacles for that one. But once I changed the Q and R values and all those other parameters, it started to avoid the obstacles, and it even tries to follow the path. This blue dotted line is like reference path, and red path is the path optimized path of the drones that it is, and it is trying to go close to the blue path because that is what I want. And like it is controlling in a very good way, very smooth way. You can also see the what much of acceleration and velocity it required to avoid the obstacles. You see over here the acceleration is like quite high because it needed to avoid the obstacle in the path, and successfully it avoided the obstacles. So like what I'm saying is like it is really important for someone to know the linear algebra and matrices and how to combine both of them, uh, just to identify the system, analyze the system, and get some useful result from the systems. You can use this one in real life and real time, and this is really helpful. So I hope you guys know the importance of the linear algebra in real life. I will show you some of more things let me go suppose there is some ocean, or there is some sea, and over here there is island, and so you want to come with your boat to the island, okay, and but the problem is that there will be wind coming, and there will be some kind of a disturbance. It's like water there and due to wind, you will not always go to the intended directions. You will be shifted over here, or you will be forced to go on this direction. Now you to find the probability that you will reach in this time, or you will only take like half an hour to reach this island. So even for that one, you can use the linear algebra to estimate the time, and estimate the path, which path will be the better one to take. But for that one, you also need some previous data, so that you can predict those things. And once you predict, you can even use the real-time data and solve the problem at real time. And that is how AI and machine learning also works. So I also fascinated how control system and dynamic system is much more closely related to the AI and machine learning. It is really fascinating. Also, suppose there is a robot, right? And suppose, to simplify, we make a grid for the space. Suppose you can mostly in our real world, the space is like this one. There is infinite number of grid, means you can go at any place from here to here, and this is also a grid. But I have just discretized this one to simplify. So suppose you want to go from here to here, right? And there is multiple enemy over here. So if you touch them, you are gone. You won't be able to reach your destination. So even if you want to solve the problem like this one, you can use linear algebra and matrices to do that. But there's some methods like dynamic programming, dynamic programming, and there's also other method from the computer science. There's A star search algorithm and other algorithms which will solve this problem. But if you see dynamic programming is from the control systems, there's also other programmings differential dynamic programming, and there is LQR method. All of these uses the linear algebra and matrices, but also combined with the probability and statistics. So I would say that if you are very sharp at probability, statistics, algebra, and but matrices, then you will excel in these kinds of problems very easily. I might show you some of my sample work in very details in the upcoming videos, but I think this is enough. I just give you some idea or insight about how linear algebra and matrices is very important, and why it is really important in control system and dynamic systems, and to solve the real world problems. And please don't forget to subscribe. Please subscribe. Okay, thank you.